Okay, so we are still going back to video 4H. 4H was where I sort of did a bunch with bricks on boards and everything, and so we're still going to be using data from that. And now we're going to talk about how I let the brick just kind of slide down the incline, and I measured that the time that it took the brick to go 1 meter was 1.4 seconds. Okay, so let's go back and do our good old XT, VI, VF, A, and we can actually solve all of that. My distance was 1 meter. My time was 1.4 seconds. My initial velocity was 0 meters per second. And what I really want to find, actually, I actually don't care about VF. We won't take the time. I want to solve for A. So we have x equals VIT plus 1/2 AT squared. And we're going to solve that for A. Remember that this whole thing is going to be 0, so we don't need it. So I can say A is going to be 2 x over t squared. So my A is going to be 2 times 1 meter over 1.4 seconds, and then again remember to square it. So 2 divided by 1.4 squared is going to be 1 meter per second squared. That's going to be my acceleration, 1 meter per second squared. Now, some other things we know about that brick was the weight of the brick was 16 newtons. Well, if I want to figure out what the mass of the brick is, in a previous video we said that weight is mass times 9.81 meters per second squared. Well, so that means that if I want to find out the mass, I'm going to take the weight, which is 16 newtons, and I'm going to divide it by 9.81 meters per second squared. And so I've got 16 divided by 9.81. I get 1.63 kilograms. And that is the mass of the brick. Now, ultimately, the net force on that brick is going to be that mass times that acceleration. That is the actual acceleration of the brick. So the actual acceleration of the brick times the actual mass of the brick is going to be the net force on the brick. Probably if I did it out, let's see. Yeah, it'd be more like 1.66 if I avoid rounding. I'm sort of playing very fast and loose with significant digits here. Okay, so now let's analyze this from the perspective of the vectors that we found. The vectors that we found in this situation right here. Okay. So I want to talk about if I have an incline of 22.3 degrees, and I've got an object sitting on it. I'm going to have another triangle that looks like this. That's going to be a right triangle, that's going to be a right triangle. This is going to be 22.3 degrees. Now from the previous lecture, which I'm not going to, we figured out this is 16 newtons. We measured that in the lab. Now we found force normal. Force normal is 16 newtons cosine 22.3, and so we figured out that that was 14.8 newtons was force normal. So that's force graph, that's force normal, perpendicular to the surface. Force normal is perpendicular to the surface. And so the question, and then we also figured out that if we do the coefficient of friction, we also figured out that there was this frictional force of 3.7 newtons. Now, hang on, stop for a second here. In my previous one, previous lecture, I had force friction pointing down the incline. Now I've got force friction pointing up the incline. Why did I switch them? Because force friction is nasty. Force friction always opposes the motion of the brick. So in the previous example, I was pulling the brick up the incline. So since I was pulling the brick up the incline, friction was opposing me. So as I'm pulling up, friction is fighting me and pulling down. In this case, I'm letting the brick roll all the way down. I don't have any, I'm not pushing or pulling on it. Gravity is going to have it move in this direction. And since it's moving in this direction, force friction is going to go in the opposite direction. So the different direction of movement causes a different direction of force friction. So my question is, how big is this little section of vector that I haven't calculated yet? Well, I know I can figure out from this triangle. This was 14.8 cosine, this was 16 cosine 22.3 gave me 14.8. So I'm now going to define this sort of dummy thing that's not F11, it's force parallel. And it's not a real force. It's a funky sort of not real force. It's basically what's left over when you add force gravity and force normal. They don't quite add up to zero. And so this is that don't quite add up to zero part. And I'm going to find that that is 6.07 or 6 newtons. So force parallel is 6 newtons. So this whole thing in here is 6 newtons. Now, out of that whole thing, we're going to take away 3.7 newtons of it, and we're going to find out that I should have come up with a force net of 2.3 newtons. So that's the force net that I should have gotten, and I measured, call that, so that is calculated one way, method 2, and then from this we have force net equals 1.7 newtons, and that's calculated method 1. And so you see that they don't quite agree, which is what I'd expect, because I'd expect there to be a lot of error in this as a whole. But they're relatively close. So there's an analysis of a brick sliding down an incline.